Lin Chung Hong from Yale University of Technology, and today I will talk about my paper that is extracting brick component from a layer scan bird cloud. This work with my colleague Rorik Lindebus. So in this presentation, first we will brief up the motivation and the scope of work. And after that, we will present the proposal method, how we extract the component of the bridge. And then we will show the preliminary result. So you know that is usually a lot of the bridge, they had a problem like collapse, damage. So during service, uh, they had a damage. So they need the 3D model for management, for inspection, and for assessment, but it's not available. So as you know that in US, they get around more than 600,000 bridge damage, and in which that is around 23.5% that is slab, and in UK more than 40% the slab. So that's why our study focused on the slab bridge. So in this proposal that I will use the both spatial information of the board cloud and the contextual knowledge of the bridge component like location, orientation, and such to extract the component. So here we extract from the substructure, and then we go to the substructure. So the first is superstructure and then a substructure. So we go to this order. So the first thing that the point cloud of the whole bridge is decomposed in 2D cell, and the cell will be in the S and Y direction, and you can see the 2D cell may contain the point cloud of multiple structure like ground, pier, and then we split the point cloud in we define the local surface in each cell, and then we use the cell by region growing. We extract the point in the surface. After that, based on this method, so we see that the point cloud of the top surface of the superstructure that is located on the first bit of the cell. So we use the first bit, we can extract the first surface, and then we can use the second. We can extract the bottom of the surface of the superstructure, like the bottom of the slab, and based on that, we will extract the surface located between the bottom and the top. So we call the intermediate surface, and this is the method. So we use the based on the location surface, we can extract their component. So now we had a superstructure involved the top, the bottom, and the intermediate. So and then after we extract the substructure, we can deactivate on the boy, and the boy inside the cell we can calculate the height and the gap. Based on that, we can classify the cell it contain the boy cloud of the substructure or not. And after that, we clustering, and we can define, okay, that is cluster contain the boy cloud of the abutment, which one it contain the boy cloud of the beer. And then we use the voxel-based region growing, we can extract the surface of the abutment or the beer. And also during that, here, so we can extract the abutment, and we also implement some contextual knowledge to remove the incorrect surface. So you can see that we call the connected surface component on quantum that it can discard the unrelated surface. And here, for example, this is the example that we took the scan of the bridge in Germany. So the bridge is long around 20 meters and with a wide around 9 meters. and we scan by the scan B20. Oh, I'm sorry. And here we can we decompose to the cell, and then we apply the techniques. You can see that is the first image that is decompose, and the bottom 3 image that is the surface of the top, and the bottom and the intermediate surface of the substructure. So and that you can see we apply similar, and we can get the point cloud of the abutment and the pier, and we apply the voxel-based region drawing, and we can get the final surface of the component. So based on that, we just visualize evaluation, and we show that 100% of the component of the bridge were extracted, and the processing time for total around 650 seconds for the data set, around more than 28 million points. So the interesting that we propose the method that use the spatial and the contextual knowledge to extract the component, and our method will also work on the sub data set, so it can do efficiency and robust. So we not deal with the strong with the parameter to select the good parameter for extraction component. So this is my presentation. So because we had a very limited time, so I'm looking forward to discuss with you after presentation. Thank you
so much, Lynn. And so would like also to invite our next presenter, Maliha Honek, scan to BIM in the semi-automated generation of material passport for an existing building. Yeah, Maniha, do you hear me, Maniha? So it's still, so yeah. All right, so again, so welcome. So we have our second presenter, Maliha Honek. So he's gonna talk about scan to BIM for the semi-automated generation of material passport for an existing building. So, so please, Maliha, go ahead, please. Maliha, unmute your.
Sorry. Okay, now. Okay, sorry. So we can just skip the slide. That's fine.
No, you're good. Yes, good. Yes, go ahead, Maliha.
So my research is based on the research project SCI-BIM, which stands for Scanning and Data Capturing for Integrated Resources and Energy Assessment using Building Information Modeling. It was funded by the Ministry of for Transport, Innovation and Technology. And we have worked with partners from Vienna University of Technology and also from industry. So buildings in the European Union are responsible for 50% of all extracted materials and also for 35% of greenhouse gas emissions. Moreover, the construction sector is the largest consumer of raw materials. Therefore, the aim of the European Union is to reduce waste, use less virgin materials, and also enhance the recycling rates. But the problem in the building industry is that there is lack of knowledge on the material composition of the building stock, which is the main obstacle for recycling of materials. Therefore, we need new tools and methods to create a secondary raw materials cadastre, and therefore we propose a material passport. A material passport is a qualitative and quantitative documentation of the material composition of a building. And it shows, for example, the allocation of materials, the amount of materials and what kind of materials there are, also the share of recyclable and waste materials, the environmental impacts, and also the separability of materials. And the objectives of these papers are to test the semi-automated workflow for the generation of a material passport. Therefore, the first aim is to create a BIM model based on a point cloud. The second aim is to integrate the materials information into the BIM model. And the third aim is to compile a material passport of this existing building. And this existing building is a lab and office facility of Vienna University of Technology with a total area of 1,265 square meters. It's a single-story building which comprises of 3 areas. We have an office, lab, and storage area within the building. And the workflow works as follows. We have laser scan for the geometry, and we have a ground-penetrating radar scan for the materials. So based on the laser scan, we have a point cloud, which is then being reduced. And based on this reduced point cloud, a BIM model is created. The BIM model is created on the one hand manually, and on the other hand, it's being created semi-automated. And based on the element IDs, the GPR scans are mapped to all the elements within the BIM model through the IDs. And then we have a BIM model with material composition. Based on this, we link eco inventory database to create a material passport. And the first is data acquisition within the methodology. It was conducted by 3 surveying companies, company 1, 2, and 3. 1 and 2 were responsible for laser scanning for the geometry, and company 3 did the ground penetrating radar scans in order to obtain a material composition of the building. And laser scan is an established geometry acquisition method, whereas the GPR is a novelty. The GPR uses an electromagnetic wave as signal carrier, which is radiated into the wall by a transmitting antenna. On the right side, you can see a picture of a radar of a wall, radar picture of a wall. And also points to beam has been applied, so the semi-automated algorithms for the generation of a BIM model were created. And the further steps will be an automated integration of the materials information from the GPR. On the picture, you can see the first IFC model of the use case. And the material passports method, it is based on an Austrian method, the IBO. It's assessing the share of recycling and waste at the end of the life cycle of a building. And it gives recycling grades from 1 to 5, which are assigned to the materials within the building elements. And this is the first result of the GPR. So this is the floor plan of this use case. And we can see that the GPR can distinguish between the materials. So for example, in dark gray we have a concrete wall. And in orange, for example, it's an interior wall. And this is how it can be the measures can be distinguished, all the walls. This is the first result of the material passport on a wall, on an outside wall, 0.6. We have the input parameters, which are the density, surface weight, thickness, area, and mass. These input parameters are obtained from the BIM model and also from the GPR scans and also from demolition experts, which were on site. And also the results, we can see that we have the recycling grades from IBO. We link them to each material, each layer of the wall. We have information about the quality of the materials from the demolition expert. And then we optimize the recycling rate, and in the end, we obtain the share of recycling and share of waste materials. So to conclude, the methodology for generating a BIM-based material passport for an existing building was tested. The scan-to-BIM process still requires some optimization and automation. And the workflow is also confronted with various manual steps, such as integrating material information from different sources. Also, the presented workflow serves as basis for generating a secondary raw materials cadastre, which could enable the increase of recycling potential of existing buildings. And it would also help to realize urban mining strategies for cities, for example. So our future work, we just received a grant for a new research project, which is BIM Stocks, digital urban mining platform for assessing the material composition of building stocks through coupling BIM to GIS. Thereby, we will improve the applied GPR technology and also use machine learning algorithms for determination of the material composition of building elements by using GPR. So you can get some further information about our research projects on the homepage, or you can contact me by email. Thank you for your attention, and see you maybe anytime. Bye.
So, yeah, thank you, Maliha, for the presentation. So we're looking forward for the third presentation today. John Han Wen, optimization of a user-involved floor layout recommendation. So we are waiting for the third presenter. Yeah, we're waiting for the. I'm not sure we have the third presenter or not, so let's double check. Yes, so, okay, excellent. Thank you. Please go ahead.
Actually, is not here. I don't know why.
Oh, the third presenter is not here. Okay, so then
No.
we have to move.
Let's move to the number 5.
Number 5.
4 is also absent right now.
Sure. All right. Okay.
Please, number
so let's
5.
now
Okay?
have the. Yeah. Okay. The 5. The listed number 5, the presentation, which is the impact of COBE on design activities, by Diaby Bose. Hopefully, I got that right. So I hope we have the presenter.
Hello.
Yes. Hello.
Hi.
Hi. So, yeah.
Okay.
Go ahead.
Should I get started? Okay. Hello,
Yes,
everybody. This is Devi from University of Florida, and I'm going to be presenting my research on impact of COBE on design activities. So moving on to introduction. So the construction operation building information exchange data, short for COBE data, helps maintenance and asset managers to quickly operate their facilities at a lower life cycle costs. And since its inception, COBE standard has been adopted in many projects across the globe. And while most of its technical hurdles have been overcome, the changes that may be required in design activities to meet the data quality standard
I guess Meliha is out of business right now. Let's wait a bit if he enters again. Okay.
Actually, I think Dalby is here. I'll put her again.
I don't see my presentation.
Yeah, it's not up yet. Yeah.
Oh, okay.
It will come. It will come soon. Yeah.
We could move on to the background. Okay. So the COBE standard was created and tested by the US Army in order to define the subset of construction handover data needed by facility managers. And to make sure that COBE data is successfully extracted, a two-stage quality control process is carried out. First is verification of the data. This implies that the COBE data generated must comply with the standard format and is a technical check for errors like duplicate room numbers or missing space information. And second is the validation of the data, which checks that the information on the contract document is the same as the information provided associated in the COBE file. But despite these checks in place, it is challenging to capture asset information in COBE format for reasons such as COBE specification, confusion about format, and user understanding. Um, as for the objective of the study was to investigate if the changes and practices of the current design softwares used are required to correctly deliver standardized building information. And the methodology, the case study was carried out on a 500,000 square feet academic building at the University of Florida. Revit models for each discipline were created by the graduate students, and a two-step quality control check was done on the data. So moving on to the discussions, first is the verification errors. These are the technical errors in the exported COBE file that were faced during the case study, such as missing room numbers for fixtures that were above the ceilings. Second is the validation error, which, as discussed before, is not a technical error, but a check to make sure that the data is in the COBE file are in compliance with those in the contract documents and schedules. And all of the discussions from here on will be a validation error. So the first validation error was the missing components. It was found that various plumbing and fire protection fixtures were missing from the respective trade models. Second was missing component type parameter for various mechanical and electrical fixtures were either missing or were incorrectly identified in the model. Third is the incorrect object type. So the windows that were called out in the design drawings were actually modeled as curtain walls, and COBE couldn't identify that. So the research team had to individually input all of the window data into the into the curtain walls to make sure that it's represented accurately in the exported file. And next is the scheduled attributes. It was found that attributes like room finishes, door size, NPF, fixture model numbers were not captured in the model. And again, the research team had to input those information into the model. And finally, the implied scheduled attributes. As you can see on the screenshot, there are two different parameters, such as the manufacturer name and the model number, are grouped together in one column. So this requires user interpretation, and it cannot be extracted as is into COBE format. User intervention is required first. So this is something that we are trying to explore and see how that can be fixed in the design documents. Moving on to the next slide. Finally, the limitations of this case study would be that the case study was carried out in a single building, reflecting the design choices and conventions made in a single set of design drawings. And more case studies on different facilities will identify additional conventions that will add to the findings of this case study. And secondly, the models were created by graduate students and not industry professionals. But having said that, this BIM technicians who are required to use BIM tools are usually less well instructed than those of the graduate students at the University of Florida, and as a result, we may expect many of the conclusions reached are directly relevant to new modelers. And to conclude, using softwares like Revit that have undergone rigorous COBE compliance testings, teams can easily export design files that will meet COBE QC quality control standards. When information is exchanged on design drawings, it is largely based on readers' ability to interpret the content and cannot be extracted as is. And lastly, addressing the traditional data representation conventions in design drawings and schedules must be carried out in simpler projects in order to apply them to more complex projects. Finally, as for recommendations, first, it's important to provide proper training to model draftsperson to make sure that the model is COBE compliant. Second, the BIM models must reflect the products and equipment that are found on the drawings and schedules. Most of them were found to be missing in our models. Next, the BIM modeler should be expected to update the models regularly as changes are made throughout the life cycle of the project. And finally, drawing schedule data must be made explicit, eliminating multi-valued numeric attributes. Thank you.
Diaby Jose, thank you for the presentation. Okay, so good news. We have now the third presenter is here to present, Jonhan Wen. So optimization of a user-involved floor layout recommendation system on the operation stage. Okay, she's here. Sorry. Yeah. Yes, go ahead, please.
Okay, so first of all, sorry to be late. I mistook the date for this presentation. And my name is Jun Han. I'm a previous intern student at the Luxembourg Institute of Science and Technology. And I'm very happy to be here to present to you about my flow layout recommendation system, together with Ali Daher and Selva Siddiqui. So my presentation will be basically from 5 perspectives. I will state the problem and then introduce my methodology and how I apply it. Then I compare it with our decisions from traditional methods, and then goes to the conclusion. So the research question of mine is to optimize the interior layout of a rough cast office buildings, of which has its structure and its separation. And the concern is the comfort of rooms and the practicability of the plans. Additionally, we would like to introduce high level of user participation during the design of the floor layout. So, which means the design would result in highly customized. The research objective is mainly from several points listed here. First of all, the characteristics of the spaces in the office building should be investigated, such as the daylighting, noise, views for the comfort level, and so on. And then from the user's aspect, their preferences regarding these criteria are also collected, and somehow they need to quantify it if they don't have really understanding about the values of the simulation. And then it forms some physical spaces and some where some functions should be allocated inside. Therefore, this allocation of the function and space pairs are the main object to be optimized. After the optimization, the recommendation will also be visualized in certain software so that the users can use an interactive system to customize the optimization and also to select based on their other latent criteria. The hypothesis of the research is that first of all, the design is for the newly built building, of which the structure of the floor layout is already designed, and there could be some non-structural walls which can be removed if it's required, and then it forms new rooms by merging the others, and of which the characteristics could be estimated by the previous simulation. And it is assumed that the simulation results is a good representation of the comfort of the rooms, even if the layout of the functions are changed. And the level of room adjacency are defined in a qualitative way because it's hard to measure. Because it's hard to describe by numbers. And the evaluation of user satisfaction of each function space pair ranges from 0 to 1 according to a threshold and optimal range of their use of the requirement from the user. So the methodology mainly separates the working pipeline into 4 parts. First of all, the expert input regarding the space features and the space adjacency are collected and simulated. And then the customer input about the priorities of the room allocations. The favor of the features are also collected based on reference of the expert input. Then after screening, it goes to the plan creation and optimization, where the allocation is based on a tree allocation algorithm, and then overall satisfaction of each plan are calculated, and the top 10 plans are saved and recommended to the customers by means of visualization and some manual modifications on the plan with the interactive system. The screening of the data basically from the value of the simulation results, such as the external noises and daylights, where the customer will have their threshold of what they really don't want to have with their functions of rooms, so that those spaces that have their simulations in this unfavored range are screened out of the possibility. And the rooms that are allocating are separated into priorities. So the tree allocation algorithm is is used within each priority. For each priority, there will be separate plans that are visualized with a sliding screen so that the customer can decide among these 4. And then with selecting one plan from priority, the tree grows in with the rooms that are categorized in priority B, and then form the final plans. They're also visualized in the same model by fast rendering through Grasshopper. And the scores are also shown in the 3D model that could be seen in the bottom right. The scores are calculated based on fuzzy logic if the criteria are quantitative and continuous. Otherwise, for the criteria such as the adjacency level, which are discreted and qualified, it is scored by a scoring dictionary, which gives some punishment if there's if the final plan is above the requirement from the customers. And we also conducted an experimentation with our plans generated by the algorithm and the plans generated by the architects. Here, the first table shows how our plans performs. And in total, within total of 12 functions to be allocated, the plan consider only 10 of them because of the screening criteria, and then have most of the area and radiation suffice the function criteria. Concerning that, and the second table shows the results from the architects, where they put more functions into the allocation, neglecting that there might be some threshold that the customer would never want. And every score and some scores from the plans from the architects are relatively lower than that from the program. The challenge of this problem is to formulate the information from simulation to be understandable. And also the tree allocation algorithm is developed to deal with the enormous number of possible plans regarding the space function pairs. And the optimization of the overall plan is considered as to optimize the satisfaction from the users. The conclusion of this research is, first of all, we propose a workflow of the interior layout recommendation system, where the system utilize the results from simulation, from customer preferences, and so on. And this workflow also integrates the building simulation, which are one of the key competencies of building engineers, into design phase, so that the expert could participate more. As well, the user participation is also integrated into the design phase, which means the plans are highly customized according to their specific needs. In the end, we provide the user interface to be interactive and dynamic, so that it can have a real-time change and optimization. Further suggestions of studies could be the approximation of resimulation results and applying some reinforcement learning algorithms to make it more with machine intelligence. And as now, so far from now, the programs are executed on different platforms. For example, the algorithm is on Python and the visualization is on Rhino and Grasshopper. So we expect an integration of the entire process so that the interaction could be easier with the customers. Thank you for listening to my presentation, and please let me know if you have any questions.
We have now the presentation number 6 by Adam Koiski. So talking about automating BIM objects, right?
Yes, that's right. Hello. Oh, Barry.
Yes, hello. Yeah, optimizing. Yes, hello. Yeah, welcome, and would like to invite you to start your presentation, Adam.
Thank you. Hello and warm welcome to our presentation on object-based lifecycle costing of cleaning operations. My name is Adam Piaskowski, and I'm a recent graduate from Aalborg University, and this research has been facilitated by Professor Kjeldsvit. Next slide, please. So let's talk about money. The repetitive nature about making cleaning a primary cost generator in facility management, and this is especially true at a city or a country scale, where we're talking about millions and perhaps billions of potentially mismanaged or unoptimized taxpayer money. The potential to save money is especially true in hospitals where operational costs exceed procurement costs just after 3 years of operation. A regular office spends about 30% of its FM lifecycle costs on cleaning. And because it's a broad domain, we're only focused on interior cleaning. The design of permanent structures requires a cross-disciplinary collaboration, i.e. facility management teams instructing the designers on what works and what doesn't work, and what is practical and what generates unnecessary costs. And to make a cost-effective impact, we should talk about cleaning early in the design development, where the ability to influence design is the greatest. Though collaboration is not always possible, and even so, can it help estimate the cost? Well, the reality is that every building consists of thousands of objects, each requiring a different cleaning approach. And the costs of that are hard to quantify solely on room areas and occupancy rates. And we're not the first ones trying to quantify this effort. The Danish building industry has proposed LCC-BUG, a tool compatible with the DGNB certification, which helps assess the economic impact of cleaning. There are, however, two problems with it. One, it's manual entry, and two, it's not very detailed because of the first problem. So as a result, we get price estimations based on gut feelings. We get the facility management to figure out the real costs, and thus risking under or overpaid contracts often set in stone for decades. And lastly, we do not consider this enough during the early design phase in the first place. So how much does it cost to get this wrong? Well, 15 minutes for a team of 10 cleaners can cost around 20,000 euros a year, or 600,000 euros in 30 years, not accounting for inflation and of a linear cost. So there's also a cost approximation dilemma relating to, at the same time, there could be too much detail needed, and it's not really available in the early design phase. So according to our research, at least objects, surfaces, and services which require physical time taking action should be quantified. And this can be done at the room or object level. So here's how we did it. I got myself employed as a part-time cleaner to learn the craft. And then we created an object database matched by a classification system to a BIM model. And then we mapped the costs and quantities to the original LCC-BIG software and the Power BI. And then we tested different objects on an early design phase model. And here's our case study model built in Revit, a 2-story office building, the one that I gathered the data over in a year. And then we tested the schema on an early design model provided by CFMOL architects for the workflow analysis. So this is a sample of object and surface database with time runs needed to clean specific objects. And then we used average salary per hour to optimize objects which were paying too well and those which weren't paying enough. So we then mapped the costs with the model, and then we extracted quantities using Dynamo, and then we used the elementary module to serialize an XML file using Python, and exported a CSV table and SVG graphics for the Power BI data display, the CSV table for the graphs, and the Power BI, the tables for the plans. So let me show you an example of how it works. Say we wanted to change our laminated desks with the new fancy anti-skid ones, where the surface is porous and it grips particles and human sweat, making it twice as difficult to clean. So we can export this data using Dynamo to Power BI. And then here we can see that the cleaning accounts for over 55% of costs just for offices, and around 30% of that cost is this cleaning of surfaces, so the floors and The remaining 70% is associated with cleaning objects. So the tables are actually of a big impact. And to the right, we can observe that increasing the cost of cleaning by doubling it whilst keeping the frequency the same, has actually increased the total cost by over 12%. And to the left, you can see that there's a big discrepancy between calculating objects on, calculating cost on objects and actually calculating cost just on areas. And the same applies to toilets, where the amount per square meter and type of components varies greatly. Choosing the method of washing, drying, and sanitizing hands has especially high variance in cost, and clean conscious design can really make an impact here. And this is quite a hot topic right now during Corona times as well. So to sum it all up, we can mostly influence the cleaning cost by selecting practical equipment during the design phase, as the physical properties influence the cleaning effort and hence the cost, as well as the accuracy of calculations can bring to light potential long-term savings, even when initial costs seem less viable. Furthermore, BIM models are especially useful here, as the objects are not always evenly distributed amongst rooms and manual counts are just not viable. And also cross-domain knowledge sharing may be necessary to develop cost databases, which currently do not exist at an object level. And for the future prospects, this research is only a start for what possibilities object-oriented cleaning can bring to various stakeholders. And if you're interested in further development of this domain, please contact me for more information. And for now, thank you for your attention.
And I think now we would like to have, open the floor for questions and answer. And we have, I think, enough time for a couple of questions. Any questions? So I don't see any questions right now in the chat. So, okay, so we have here one question. Good. So presentation 2.
Yeah.
So what is the material passport, when is it created, at project delivery, before, and so forth. Update regularly. Nature of materials might change with time, following water damage or fire.
So the material passport, in best case, is created already in the early design stage, because in the early design stage, it serves as an optimization tool where you can conduct some variant studies. For example, you can make a comparison between a timber wall or a concrete wall. So there you can make some optimizations regarding the waste at the end of the life cycle, such that you create as less waste as possible and as much recyclable materials as possible. But also, we know that the building stock, the most buildings are already being created, are already here in the stock. So the material passport, therefore, is used as a stock, as an information for the building. So it serves as an inventory of a building, which we have now applied on the research project SKIBIM. So we use laser scanning for obtaining the materials and also GPR for the materials. And this is how we then created the material passport. And for what you mentioned, the updated regularly, we have also created a gamification app, which is directly linked with the BIM model. So the users within the building, they can scan building elements, for example, the window, and then they can type in information about, for example, this building element has already been removed, and this is then being changed in the BIM model. So it is also used as a maintenance of the building. And we have already tested this gamification app. I hope I've answered your question. And
Okay, thank you, Maliha. Okay, thank you. So, any other questions or follow-up questions? Okay, so presentation number 5. So you mentioned that design models need to be interpreted so information can be understood. Apart from the classification process, what else do you think could be done to improve design awareness?
Can you hear me?
Yes.
Okay.
Yes.
So the modelers who are responsible for creating the models, it is essential that they're trained properly to interpret the design data, and apart from classifying the design data as I mentioned in the presentation, and apart from that, I think that's it that I can think of. Yeah.
Okay. All right. All right. Jose, DFD. So any follow-up questions or any other new questions? Okay. Now we have a question for the last presenter. Did you take the type of cleaning products into consideration? Some might be more effective for cleaning time, but would deteriorate faster than surfaces have a greater environmental impact. So, yeah, this for you, Adam.
Thank you. Thanks, Matthew, for your question. The case study was actually an office building which was cleaned fairly frequently. So the cleaning products didn't really have to deal with a strong chemistry to break down very old dirt. I would say that the surface area of objects is probably more important here as a factor of taking time, if that answers your question. And of course, the environmental impact of cleaning chemicals is important just in general. So yes.
Thank you, Adam, and thank you. Any further questions? I think we have also. Maybe we can take one more question. I think we have time for one extra question. Okay, sir. So we have here from Jacob Pitt for the second presenter. Very interesting project. Are there any efforts? Are there any effort to include the creation of the passport in the public, including fee models? Any initiative in Australia to do this inside this for you, Maliha? Getting more the questions.
Yes, thank you for the question. For now, there are no initiatives in Austria. As far as I'm informed, there are no initiatives. Only research projects which are working on these material passports. They are integrating the building information in GIS, for example, but you can only obtain the year when it was constructed, the building, and the height and a gross volume of the building, but not in that detail as we did it in IBM. And in our project in stocks, we will directly do this. So we will also integrate the materials information, the building information, to create a digital platform, which can then serve as basis for a secondary raw materials cadastre. And yeah, these are our plans.
All right. Thank you all. Thanks for our presenters. Really, okay. We have more one question. We can take it quickly. I think we are running out of time, but see if we can, answer this question quickly from Victor. So, do you see if companies nowadays are willing to pay for that kind of work? Yeah, yes, for you, Adam.
Thank you, Victor, for your question. Yes, it greatly depends. This is mostly addressing towards public sector. So, well, I think it could also work for companies. The issue is that at this point it requires modeling of the BIM model. In the future, hopefully this could be scanned and AI apps categorize and group the objects to streamline this process. But at this point, I think it makes sense for bigger objects where there's a bigger budget for such analysis.
Excellent. So with that, I would like to thank all our presenters for this very interesting, exciting topics. I really enjoyed all the presentations. I have many questions, but I'll run out of time. maybe in another opportunities we can chat more about those. So thank you, and I think now we have to have a short break so we can get ready for the next part of this session. All right, thank you.
All right, thank you. Bye bye.
Thank you. Bye bye. Take care.
Let me help you direct the scene.
All right. Okay.
The presenter number 4 can enter in the end of the session. Okay, he is ready for this.
Okay.
We don't have two confirmations, so we have time for him. Okay, thank you.
Okay, to present now.
Let's move on.
Right. Or we just move to the next part. Okay. All right. So I think we have now the presentation number 7. So we are having NATHIA, right? So NATHIA is going to present about machine learning for whole building life cycle. So, so with that, please welcome NATHIA to the conference now to start presenting.
Okay, thank you, Professor Nawari. Hello, everyone. My name is NATHIA, and I'm a PhD candidate at University of Campinas, Unicamp. And I will present an article with title Machine Learn for Whole Build Lifecycle Assessment and Systematic Literature Review that I wrote with Virginia Russo. And next slide, please. Okay. Build is at the highest contributor to energy demand, greenhouse gases emissions, resource consumption, and waste generation. There is an opportunity to confront climate change, global warming, and energy consumption when thinking building design. Environmental impact evaluation methods, such as life cycle assessment, are increasingly used. LCA is a methodology to quantify environmental impacts on whole building life cycle, since raw material extraction, fabrication, transport, use to end of life. However, they couldn't obtain expect benefits to the high number of parameters and certainty factors that characterize the whole build environmental impacts. Also, the high effort and cost required for conducting life cycle assessment. Therefore, it is possible to make faster progress toward reducing building impacts. Combine established environmental impact evaluation methods like a life cycle assessment with machine learning algorithms like neural network. So this article will present previous research on machine learning for the life cycle assessment of buildings. To achieve this goal, we perform a systematic literature review, and we use the protocol proposed by Kitchenian and Charters. The systematic literature review governed by the question, what are scientific research developed for architecture, engineering, and construction industry in life cycle assessment and machine learning contexts? So the systematic literature review was performed in 3 relevant databases, Scopus, Engineering Village, and Web of Science, using keywords life cycle assessment, machine learning, learn, building, and neural network. The systematic literature review was conducted in 3 steps. In the first step, we exclude duplicated articles. In the second step, the main exclusion criteria where this article deals with another study area. Finally, in the third step, we apply the assessment criteria of the dimensions of study quality. This research resulted in 15 articles. There is a 2 literature review. The researches could be classified in its optimized performance, predicting impacts, decision-making support, and developing new green building assessment index. The machine learning algorithms are classified into supervised learn, unsupervised learn, and reinforced learn. The algorithms found in articles were artificial neural network, linear regression, support vector machine, clustering, genetic algorithm, and others. The articles classified as to optimize performance, the others used artificial neural network and genetic algorithm to explore different scenarios of building, considering energy, cost, or environmental impacts. In the articles classified as impact prediction, the authors developed a method to predict life cycle environmental impacts, energy consumption, food consumption, and global warming potential. Some others focus on buildings, others focus on eject molding and road pavement. The machine learning algorithms used were artificial neural network, Bayesian network, high Markov model, multiple linear regression, and support vector machine. These algorithms could be reduced computation time with high precision of results. The last order's impact prediction focused on life cycle assessment methods. The first developed a new algorithm called Predict used mainly for life cycle assessment, and the second used artificial neural network to uncertainty analysis. Lastly, the articles focused on machine learning used to decision-making support. The objects of these studies were brick, construction material, and buildings. The algorithms like backpropagation neural network and clustering were used in these studies. So machine learning is mainly used to predict impacts. The most researched environmental categories were energy consumption and global warming potential. And the most used machine learning algorithm was artificial neural network. ANN was used mainly to optimize building performance and impact prediction. These models offer a better and more reliable decision support tool, reducing uncertainties in life cycle assessment. Also, there is a significant reduction in simulation time. Other algorithms like genetic algorithm, clustering, and BPNN can be used to estimate energy consumption, assist in choosing environmentally building materials, distinguish classes of materials based on their environmental performance, and to assist in design decision-making. Advancing LCA and NL area can contribute to calculation and analysis building environmental indicators, as well as in developing and improving LCA methods. The reliable data and NL combination will produce an unprecedented change in speed and accuracy of LCA. We want to thank the support provided by Unicamp, CAPES, SCE, and PICI. If you have any questions, we'll be happy to answer them. Follow our email. And thank you so much for your attention.
All right, thank you so much, Natalia Barron.
Thank you.
So the next speaker, and so I think speaker number 8 is the 8th presentation. Is Yu Shin. So this is the advanced BIM platform based on a spoken dialogue. Yes. So this is also from our school. Yes, please go ahead, Shin.
Hello, everyone. My name is Sang Shin. I am a PhD student in University of Florida. Today, I'm going to talk about my ongoing research on advanced BIM platform based on spoken dialogue for end user. In recent years, in the field of next slide, please. In recent years, in the field of architecture, engineering, and construction, these fields are trying to utilize AR, VR, and hologram to check design and to find design errors while comparing to BIM models in the real construction site. Next slide, please. So my research question, next slide. So my research question is, how can BIM be used more efficiently in this changing environment? In this study, my answer is to apply automatic speech recognition system into BIM software. Next, please. To know the possibilities of the research, I reviewed previous studies. Among these studies, I would like to talk about 3 representative studies. These studies have similar purpose and methodologies. Next, please. Next, please. The main purpose of our studies are to find BIM data using human voice with each proposed systems. These studies can be divided into 2 parts based on the input type, keyword-based comment, and natural language queries. However, all studies have the same data approach method that are called keyword matching. Such keyword matching based approaches can come up with a problem when results are given to users. For example, when users want to find word information using their system, the result can show every single piece of data with the word in it. That's because there are already many properties that are used by the word as a keyword. This result will not be exactly what users want. Next slide, please. So in my research, I'm going to try to improve the previous study's limitations by applying a semantic-based approach method, which helps the proposed algorithm to better understand natural language queries, as well as by using structured query languages. It enables users to manipulate BIM data. Next slide, please. This figure is overall framework for the study. This research consists of total 3 modules. Each modules are interconnected each other. Next slide, please. From this slide, I want to talk about each module's process in detail. In the first figure, it is module 1 process, and it is similar with natural language processing. Here, I'm going to try to make a difference by applying the concept of ontology in terms of BIM perspective. In the next figure, it is a module 2 process showing how to change natural language query to structured query language. I'm going to show a more detailed process for this in the next slide. Next slide, please. This is a simple example showing the process. The first box means the output result of the module 1 process. It is the analyzed natural language query. There will be some stop words and non-stop words here. Non-stop words will be changed into structured query language according to each step. In the end, natural language query will be changed to structured query language format, and it will affect directly in manipulating BIM data. This process is the last module showing the process of changing BIM data to the relational database format. Using Dynamo, I'm going to extract BIM data to CSV format, and using Python or Java programming together, I'm going to change the format. This module plays an important role in creating an environment in which structured query language can be used. This figure is the overall architecture for speech recognition-based building information retrieval in BIM. I'm going to set a specific scenario to proceed with the research. With the scenario, BIM model will be made. And then the proposed algorithm will be applied into the BIM model to conduct test cases. In conclusion, contribution in this study are to provide a semantic-based BIM environment in order for users to manipulate BIM data using their voice, and to provide a way to transform an expert-oriented environment to client-oriented environment. Like any other studies, this research also has some limitations. First, the process of methodology is a little bit complicated, and since it is scenario-based, it has limitations that it does not deal with the whole data, but only deals with some data. Thank you so much, everyone.
Yeah, thank you so much. Thank you so much for the presentation, Shin. I think we're looking forward to the next presentation, number 9. Automatic generation of architectural layout using genetic algorithm by Garbuzu in BIM. Hopefully, everyone is ready here. Yes, so now the floor is yours.
Thank you. Hi, my name is Garbuzu from Ryerson University here in Toronto, Canada. Together with my professor, Jennifer MacArthur, from the Department of Architecture Science, we're here to discuss how automatically generated floor layouts that have been optimized with genetic algorithm can be utilized in BIM. So why space planning? It is a crucial step in construction projects as it directly affects the outcome of the building. Here shows a traditional representation of how it is usually done, starting with hand-drawn diagrams, which is often arbitrary, time-consuming, and labor-intensive. And with the rise of automated design technologies, repetitive tasks such as floor layouts can now be assigned to computers. This research focuses on the preliminary phase of a construction project, intending to generate spatial relationship diagrams as the guidance for future architectural design. So first, we created the initial room layout using circle packing algorithm. Once that is created, the goal is to find the most spatially efficient layout, and it was done using 2 machine learning techniques. The last step is to transform the diagram into usable data in BIM using Dynamo, resulting in a true architectural floor plan. So for our case studies, we adopted the case study approach, and it was initially tested with circle room creation algorithm. The initial placement was optimized using 2 machine learning techniques. Then we square off the geometry to create a more realistic diagram for room layout. Finally, it was translated into BIM using Dynamo as a plugin. And to accurately examine and improve the space planning technique, a control scenario with defined programmings is adopted. In this case, a topology of a small-scale shopping mall was chosen, which includes a set of 17 rooms as the primary programmings required. The proposed sample site is said to be a 35 meter by 35 meter square. And all room information is processed through a series of functions coded using Python. And the order within the list is determined by the number of adjacent rooms which are acquired. Can we go to the next slide, please? I think it's stuck on this slide. Yes, so here you can see that's the room plotting sequence example. And the script will follow this sequence to iterate through all the rooms in the master data sheet until all the rooms are placed in the diagram. So all rooms will look through this cycle and determine their order. Rooms are separated into 3 arrays: N, rooms that are currently being placed; P, the rooms that are placed just before N; and D, all other rooms that have been placed already. As each room is added to the diagram, there are 2 rules that the function needs to satisfy. First, they cannot exceed the site boundary, and second, they cannot overlap with any other existing geometries. To represent the rooms, circles are chosen due to their flexibilities. Rooms are placed following their predetermined order from the room plotting sequence. The position of N is offset from the center P1 by its required dimension and rotated around P1 until both rules are satisfied. So here are the results, coming up next slides. And you will see the results from the earlier trials. So this represents the most common errors that can occur. So as you can see, during this phase of the research, accuracy was compromised to increase the variety of outputs. However, since the diagrams generated could not reach the ideal results, methods of machine learning were applied to achieve a more optimized layout. So a common approach to genetic algorithm was adopted, where chromosomes of two parents were selected to produce children containing genes from both parties. The genes are represented by the angle alpha that can be mutated, since the goal is to achieve the smallest footprint. The fitness calculation is based on the current bounding area. The smaller, the better. However, the optimized algorithm was stuck in the local minimum, and to achieve global optima, simulated annealing is introduced. The objective is consistent, but with an additional randomized factor of probability, calculated through Boltzmann factor. This benchmark for acceptance is randomly generated to avoid termination at local minima. And in this slide, you can see the result of the optimized layout, where the boundary in blue is at its smallest. This version of the room layout contains the least amount of dead spaces while satisfying the two requirements: no overlapping circles and staying within the site, which is outlined in red. So circle diagrams are the schematic representation for room layout. To generate a workable floor plan, the graphic must be translated through shape-finding functions. The edges are generated by offsetting the coordinates of the centroid by this radius, creating equal length edges populating the site, which is easier to work on for later research. Due to the difference in geometry, overlapping edges are inevitable. They can be detected by comparing corner coordinates of all rooms to find where two might intersect. Once that is found, the corners will be shifted to avoid collision. The resulted diagram now has no overlaps between rooms while maintaining within the tolerable contingency, which is 5%. To translate room data developed above to architecture floor plan, visual programming language Dynamo was used to allow users to access to the result through BIM software. Due to the fundamental deviation in programming languages, Dynamo uses R and Python instead of more standard CPython. The polygons were extracted as a list and can then be read. The result from the first attempt had many errors, and the optimization algorithm achieved an efficient footprint while satisfying both requirements mentioned. During squaring, overlapping in other rooms were noted and were resolved. The final floor plan implemented in Revit achieved all desired spatial requirements, yet remaining a buildable geometry. So from room datasheet to BIM, this research has achieved a streamlined approach to room planning. Circle packing was an ideal point to begin, but failed to provide usable polygons, which was resolved by squaring. Using machine learning techniques during this process has been highly effective. However, the adaptability can be improved within the BIM environment. The practical implementation of this work are significant. For architects, layout automation tools can increase the efficiency of design. Now they have more time to focus on creative tasks, thus enhancing overall design quality. Alternative fitting functions and multi-objectives should be considered to suit different needs depending on the functionality of space. For example, Autodesk has conducted a research project using generative design to reimagine their Toronto's office. As a result, thousands of design options were generated, and they were able to pick the one that fits all their design needs. This is what we hope to see more in the future, pushing the limit of the use of automatic computation for architecture. And that's my presentation. Thank you.
Yeah, thank you. Thank you so much, Carbozu, for this interesting topic. I'm really excited about this topic myself as well. But now we have the next speaker for the presentation number 10, Victor Farias, analysis of urban isolation of engineering project using BIM. Okay, so with that, the floor is yours.
So, hi everyone. I'm Victor Farias from ICCCBE, it's the state of Ceará, Brazil, and I'm gonna present the analysis of urban legislation of engineering projects using building information modeling, BIM, with the aid of graphic programming. Can pass. So, feasibility study is a preliminary design phase necessary in any civil engineering project. Basically, what it does is to analyze if what you want to build is possible in the selected terrain that you have. And so you use many kind of steps to analyze the viability of the building. One of the steps is to analyze the legal parameters, and that's what I'm going to focus on this paper. The urbanistics law determines some parameters that limits the geometry of your building, the volume of your building. But there are too many variables, and with too many variables, too many possibilities. So it's hard to do it by hand, to do it in the common way. So we want to make the process better. We want to make it more efficient. So that's when enters the BIM and visual programming. So here in BIM, we use the Revit software. It will do the virtual simulation of our model, of our building. And as it is parametric, you can change variables and you will see the difference of the model in real time. But the software is limited, so we use visual programming, in this case, the Dynamo that is applied to Revit to increase the potential of the software. So it will do all the necessary calculus according to the law to show us the maximum building possible. The objectives of the research, to make it clear, is to evaluate the urban suitability of buildings in terms of land guidelines using BIM technology and a Dynamo. We want to make the process of analysis better, so more agile, more efficient, easier. The land use and occupation law is the name of the Brazilian law that regulates the city. Every major city in Brazil has its own law, and we're gonna be based on these parameters of this law. I'm gonna explain more in the next slides how it works. So, for example, here we have a map of Fortaleza city, and each color represents a different zone. And what's the objectives of this law? There are tremendous. For example, to preserve the natural and cultural environment, to order the territory, the compatibility with installed infrastructure like roads and electricity, the control of urban activities like the industrial sector, the commercial sector, the residential sector. But how does it does that? Well, the law has some parameters that limits how much you can build and where you can build. But for this paper, we're going to use 4 parameters. The maximum height of your building, the occupancy rate, that it's basically the area of your building within your terrain, like the shadow of your building. The setbacks, that are the distance of the limit of the terrain to your building. And the index of operation, that is going to say how much the total area that you can build in the selected terrain, of course. There are more parameters in the law, but for this paper, we focus just on that 4. So the methodology, we're going to simulate 2 terrains that is simulated in 2 different parts of a city, one with 90 meters times 60 meters, and others with 40 meters to 35 meters. So we're going to simulate different law parameters for each terrain, hypothetical limitations, and 2 models we're going to be generating each terrain. But we're going to change some variables within those models, like width, building height, and ceiling height. And the code should result in the greatest building allowed according to the urbanistic law. Here is a macro view of the code. I couldn't show all the code here. It's too big, but it's just to see how it works in Dynamo. This is what will make all the calculation necessary and export to Revit. You put the variables, it does the calculus, and it shows in the graphic result. In the first table, it are the inputs for the limit parameters, that is according to law we simulated for each land. And the second table is the inputs that it's possible to be varied within one terrain. These are the graphic results. The top models are in one terrain, and the bottom models are in another terrain. And you can use these models to further increase your project, to put the walls, the windows, the floors, but every model are according to the law. This table is a quantitative result, and you can see, for example, in the last line, the total of apartments, you can see different results. So this is what we want to achieve. You change the variables, and it will still be within the law according to the code, but will have different results. So you can do it quickly. You can analyze more models and have better results. So you can have better decisions in the end. It's great for a company of buildings, for example. So the objectives of the research we consider achieved. So the process of analysis are faster and easier, but it's just a demonstrative experiment. It's just show a little of the capability of being applied to feasibility study. It's very simple models still. To be useful in real case, we're gonna need to incorporate more parameters and make a deeper study in much more cases. But we consider that we have a good result till here. And that's all. Thank you for your attention. That's all.
Thank you. Thank you so much, Victor, for the presentation. And I think we have to see, I think presenter number 11 is not, I think, here, so we have to move to number 12. So Eduardo, talking about converting Brazilian accessibility standard for BIM-based coaching using GRACE and SMC. Okay, thank you. With that, so we invite the presenter to present.
No, actually, sorry again. Wagner is number 4. We have room
okay,
for
sorry.
number 12.
All right, so we got to number 4 now. Okay, that sounds good. Okay, I'm sorry about that. Okay, yeah, so now we have to, so they have the 4 presenters, so sorry for that, came late in the sequence. But we would like to welcome, Wagner Oliveira, talking about BIM and AM for managing critical and relevant water and wastewater utilities. Thank you. So the floor is yours now.
All right. Thank you, everyone. Can you hear me?
Yes, please. Go ahead. Yes.
All right. Thank you. Sorry for my delay. Well, good afternoon, everyone from Brazil. First of all, I'd like to say that it's an honor to be part of this professional international conference, particularly leading the paper Being an AM to manage critical and relevant water and wastewater utilities assets. My name is Wagner Carvalho, BIM Master at IGEA, which is the biggest private water utility in Brazil, and Ziggurat Global Institute Professor. I am a sanitation infrastructure enthusiast with huge professional and academic background, and over the last 2 years, I'm heading the IGEA's digital twin program, combining AM and BIM disciplines. Thus, today we are here to have a teaser from BIM insights in smart water utilities within a friendly visual environment, as well as our outcomes from our practical case studies. Taking into account this, that sanitation is essential for human health, thus we deal with key infrastructure assets to global water and sewage utilities. This paper presents the digital transformation framework applied in a private utility in Brazil to meet the social and environmental challenge, combining information modeling and asset management disciplines. Yeah, Brazil having 50% sewage covered and estimated demand for investments around 100 billion by 2030. IGEA is a private group of water utilities which controls 57 municipalities, over 8 million people served, over 4,000 employees. So next slide, a key issue for us is to meet the citizens' expectation in a long-term commitment in our concessions. Yeah, next slide, please. Yeah. Asset management mandala infra intelligent program adapted from PAS 55. An effective physical asset management is the new core of the business. Yeah. and combined with BIM ISO 19650. Yeah. The water utility lifecycle representation integrating main business phase and operation phase, usually lasting 30 years in average from assumption to end of construction contract. This is the Swan Digital Twin architecture model, we are involved as smart water utility. Yeah, next slide, please. Yeah. Yeah, idea water architecture, yeah. This is the Prolago master plan, yeah, next one, please, showing the connection with the CC, with our center, control center, with GIS, yeah, and being provided us an unrivaled visualization, yeah. Next one, yeah, and combining with digital twin with our assets, yeah, we present this one in this one form. Workflow showing the integration between the hydraulic model with our database and our operations center. Calibrating the model is quite difficult and complex for us, yeah, but we are getting great results. Yeah, next one. Yeah, the asset information management is from owner operation is a key issue. And next one, you can see the difference between the 2D to the next level with being information over the whole asset life cycle, yeah, to deliver key information for our operation team. Yeah, so this one is our BIM, mental mind, yeah. Structure vision, yeah. We using Bentley open roads to analyze the class detection among different subsurface utilities. And in this one, we can see 6 different ones. Yeah, this wastewater treatment plant in high level of detail, applying the Bentley Open Plant as the key tool to integrate the federal model. Yeah. Yeah, the asset registration catalog was set in BIM platform, Open Plant Bentley. The outsourced designers worked within the configuration work to follow classification rules and attributes required for each asset type. Yeah, the graphic above shows 7% of the total physical assets in a city were classified as the most critical and relevant A, meaning the 16 assets are really significant and important to the operation system. And according to the proposal of intelligent product, they will be digitalizing. Yeah. The preventive actions business case generated by the AM and B methodologies presented, which will increase the useful life of the equipment, avoiding preventing operation damage. Yeah. So to conclude, this one shows the conflict balancing factors of cost, risk, and performance in relation to investment in preventive actions, bringing this case to the triple bottom line with SLO. It means lower environmental risk, higher quality of services for society, and economic benefit for all stakeholders, represented by a fair tariff to the end user. Thank you very much.
All right, thank you so much, Wagner. I think we have now the presenter number 12, this presentation number 12, Eduardo Alves. presenting, converting Brazilian accessibility standard for BIM-based code checking. So with that, we invite, Eduardo to present. Okay, thank you.
That's right. Thank you, Nari. Hello, everyone. My name is Eduardo. I will present this paper done with Leonardo Manzioni from USP and Eilif from NTNU, both PhDs, about conversion of the Brazilian accessibility standard through the RAISE methodology. Well, the AEC industry is highly regulated by laws, codes, and standards. The traditional process of manual verification of compliance with these rules is subjected to many variables in a slow, expensive, and error-prone process. Attempts to use automated code checking software fed from the original normative texts using BIM models built without classification systems have been unsuccessful with unreliable results. That's the wrong way. Automated code checking depends on converting the normative text into computer understandable logical statements, and also depends on the use of classification systems in the model. The checking software will compare the rules and the model data built in the same language. This research addressed standard section 6, accesses and circulation. The survey sought to answer how many could not be converted into logical statements, how many were configured for code checking, how many did not, and why. The first step in the conversion process is the T3 concept of classifying the original text into 3 types of sentences. T1 translate sentences that contain clear metrics and allow a direct connection with the rules parameters. For example, dimensions must be constant. T2 transform, there is an indirect connection with the rules parameters. They must be rewritten in logical statements, such as information presenting figures. And T3 transfer, subjective concepts such as firmly or safe conditions must be transferred for interpretation by a skilled professional. Well, about 3/4 of the information could be converted into logical statements, directly or indirectly, green on the chart. Blue represents the information that could not be converted due to some redundancies and standard definitions. The next example shows a T2 paragraph on the left converted into 3 logical statements. The highlighted sentence will be the basis for presenting the RAISE methodology. On the door pull side, there must be a free space greater than or equal to 60 centimeters on the handle side. RAISE is a synthetic analysis and semantic markup methodology. It aims to identify requirements, applicability, selection, and exception in each sentence. Requirements are easily identified, usually associated with the must imperative. It's the blue excerpt on screen. Applicability represents to what or to whom the requirement is applied, door in this case. Selection is an applicability subset. On which side of the door does the requirement apply? Exception presents what will not be subject to that requirement. RAISE markup in the logical statements allows us to build a table organized by objects, properties, logical comparators, target values, and unities. These parameters will be configured in the code checking software later. The next step is the model preparation. We utilized an existing building accessibility adaptation project and built its BIM model in ArchiCAD, classified its components according to the Omni class, and generated an IFC file. Through classification systems, the code checking software identifies each component in the model according to its meaning, as well as the door in the image on the left, the handrail in the image, in the middle image, and space, which is an important component in code checking. Here is the BIM model imported by Solibri. The spaces were classified according to their function and represented by colors. The highlighted text shows the classification rules of Solibri using the omni-class table and reading the space component. These windows represent the rules parameter settings in Solibri environment. The user informs the objects, properties, logical comparators, target values, and units extracted directly from the raise table. And after setting the rules and preparing the model, the checking software can perform the automated check. It will compare the rules data with the model data, returning results such as pass or not pass. We will see an example. Here, it returned the result not pass for that requirement of that free space needed on the handle side, on a specific door of the model, because its components were correctly set, but the design failed in this issue. However, the returned results needs attention to. A designing failure, although undesired, means that the checking process was well done. Poorly configured rules or non-configured parameters will return false positive results. Well, 46.5% of the information could be successfully configured and checked in the model. The rest could not due to some standard subjectivity or software limitations or limited access to its programming code. And finally, this chart reveals the research results. Blue represents information that could not have been converted into logical statements. In the chart on the right, dark green represents information that has been successfully configured for code checking. That's it. The authors thanks the conference committee, the participants, and audience. Thank you. Thank you.
All right. Thank you. Thank you for all the presenters today. Thank you so much for those exciting, cutting-edge topics. And now we're looking for questions, and I think we have good time to look at or examine a couple of questions today. All right, so we have now for presenter number 9, very interesting presentation. Why the choice of using circles initially? It is possible to start analysis directly. Is it possible to start directly with rectangles, for example?
Mm-hmm. So initially we started the research with rectangles, but as you know, rectangle only has 4 edges, and minus the one that is already attached to another room, we can only choose from 3 other edges, and that's giving it a lot of restriction to the plotting algorithm. And then, so we went back to see, because I have a background in architecture, I went back to how we design an architecture. We always started with arbitrary shapes, like circles. And the plotting logic behind circles are a lot more flexible because you can follow the centroid of the previous circle and rotate it around. There's no edge on a circle or infinite edges. So you have a lot more flexibility in that way. So we chose circles.
Thank you. Thank you. So another follow-up questions. Congrats. And then here, did you include any regulatory input in your algorithm, minimum room areas and so forth? You believe regulations could be used as an input to automated layout algorithm?
Actually, we did. That's our input for the algorithm, but I think it's only 1 slide, so probably it was a little bit too fast. So we did follow the regulatory adjacency relationships, and that's how we ordered our list to see which room to place first, which room has more priority over the other rooms, by counting how many rooms, adjacency rooms. So if it's like a more important area, like let's say a food court, you probably need washrooms and other amenity spaces that's around it. So that will be the higher priority in our plotting list. So the input actually directly affects the look of the diagram, and the inputs includes all the information actually that was mentioned in the question.
All right, thank you. Thank you, Gerbrug. Any questions? The questions. Okay, so very nice presentation again. Oh, all right. So another question for you today, Garbu. Very nice presentation following the call. Yeah, when circle satisfied yes requirements, could they be maintained once into rectangles?
Yeah, of course, because the location of them doesn't change. It's just the shape that changes. So, yeah, the answer is yes.
The answer is yes. Okay.
Yeah.
Good. Good. All right. Excellent. Okay. Thank you. So now for presentation, the last one, very interesting project. If some key information to determine the compliance is missing, could your system return undecidable, or in contrast with PF, could there be a tolerance option?
Yes, thank you for the question. There is this kind of result actually, and the results can be grouped according to its relevance. You can set this relevance scale also, and answering another question that I think it's related to that. It's about subjective and qualitative issues. I think a little bit of these kind of sentences are desirable in a standard to guarantee some kind of liberty to the architect, to the creation process. But I think focusing on objective statements, I think the key is rewrite the standards with organized way or some methods, some those kinds of like that presentation.
Yeah, very good. I can add to this because this is an area of my expertise. As a matter of fact, I actually wrote a book which goes into some of the details that Eduardo was talking about here, which is called Building Information Modeling, the code compliance processing using building information modeling. And this is published by CRC. It addresses many questions, even subjectivity is also being discussed, and also some of my recent work dealing with subjectivity in the building code, how this can be translated into a computable model. So, and we develop what we call the generalized, adaptive framework, which includes subjectivity to some extent, and we are also expanding on that work. So, okay. Thank you, Lord. Okay. Any further questions? Sorry, go ahead, Eduardo.
No, just I have the chance to thank you personally because I quote your work in my research.
Excellent. Yes, I know. Yes, appreciate it. Yes, thank you. Thanks.
Yes, thank you.
Any further questions? Okay, so I think you answered this question already, right? Yeah, that's already been addressed. So, okay, another question for you, Eduardo. Up, disappeared. What's happening? Okay. So another question for you, Eduardo. Very interesting project. If some key information to determine the compliance is missing, could your system? I think you talked about this already, right? Yeah.
Yes.
Already.
I ended
already addressed. Yes. Correct. Yes. Right. Yeah. That's already been addressed. Yeah. All right. So maybe I can add one question here to Garbu. I think maybe you already mentioned it. I didn't pay attention. What I know you're talking about the layout. So what about the circulations? Optimization. Is that something you can do, or not being part of the layout, design layout?
You mean collision for
circulations, like optimizing the movement from, let's say, the kitchen to the living room or vice versa, whatever. Yeah.
So that's the part that we haven't gone into yet. So this research mainly focused on how we can create a more spatially efficient layout. And I think from this point on, it will be adding more layers of like collision would be a really good way to reimagine the space, and same with like energy efficiency or even daylighting, and all those kind of elements can be added on as additional layers, but that part we haven't looked into yet.
Okay, excellent. Okay, very good. Thank you for your answer, Gabu. If not adjacent, but two rooms have to be directly connected through a common edge, would this constraint also be maintained?
Directly connected through a common edge. I don't think I really fully understand that question. Does that mean like it has to be in, I guess, close proximity?
If not adjacent, if not,
because
if the rooms have to be directly connected through a common edge.
Okay. So I guess I understand them as in close proximity. Yeah.
Yeah.
So as an input for our data sheet, we have 3 different types of relationship that we set as a guideline. So the first one is proximity; it has to be close to another, and then the first one is adjacency, to have to be close to another, and then the second one is proximity. So it gives it more of a flexibility. It doesn't have to be close, but in the close proximity. And then the last one is it cannot touch within 2 rooms. So like I don't know, 2 rooms shouldn't be right next to another. So I think all those, so all 3 requirements will be fulfilled in the programming as it's done. So I guess that I'm not sure if that answers the question. But yeah, we did consider that.
Okay. All right. Okay. I think we may have time to answer maybe one more question, and then I think we can wrap up the session. Any further questions? So I think I would like to thank all the presenters for this. I mean, as I said, all those presentations are really interesting and exciting and cutting edge. Congratulations for your achievement, and looking forward to see more of your work in the near future. Okay. All right. Thank you. And I think thank you.
Thank you.
Everyone. And, okay. Have a good day. All right. Thank you. Enjoy the rest of the day. All right. Bye. Bye-bye.